Welcome back to Code and Codes. This is the next part of our machine learning section in the How to Crack AI interview series. So hey everyone, I am Selma Kandar and today we are continuing where we left off. If you missed the last video, no worries. You can find the link to it in the description below. Be sure to check it out for foundational concepts before diving into this one. So before going to actual content, I want to show to my new viewers like what and all the sections we are going to prepare for the AI interview. So these all the sections I am divided into these 10 sections from machine learning to C and basic OS. And currently this part is the part of machine learning section where we already explored some of the topics. So make sure to watch the last video if you haven't already, and let's get started with today's content. Don't forget to subscribe and hit the notification bell to stay updated on this series. So let's start with the content. Okay. Yeah. So into the last part, I already covered the few of the topics. Okay, why the neural network had an idea, neural network architecture, their computation, and forward propagation. So in this video, I'm going to be covered this cost function into the neural network, backward propagation, gradient checking, and why weight and bias. Okay, so let's start with our first thing, which is nothing but the cost function. Okay, so before going to there, actually I wanted to tell like what and all the notations actually we are going to be used. Okay, so this thing I already covered into the last video, but in order to understand the intuitions of the neural network, so this notation actually it will help. Okay, so I will just recap the quickly. Okay, so in order to show so the first notation actually it is the L. So this notation we will going to be used in order to show the number of layers inside our neural network. Okay, so for example in this case the number of the layers are 3. Okay, 1 2 3. Then the another notation is like in order to represent the specific layer. Okay, for example in order to represent the specific layer I will use L superscript I. Okay, so if I say the L of 1 means I am representing the first layer. If I say the L of 2 means I am representing the second layer. If I say the L superscript 3 means I am representing the third layer. Okay. In the same way, in order to showcase the number of the neurons into the layer, so I will use the notation S superscript L. Okay. So if I say like the S of 1 means the number of the units into the first layer are the 3. So in the same way S of 2 means the number of the units or the neurons into the second layer are the 4, and the S of 3 means the number of the neurons into the last layer, third layer is the 2. Okay. Then the next notation is like in order to represent the activation at jth neuron into the layer L, I will represent by a superscript L subscript J. Okay, so in order to showcase like the activation at the first unit into the layer 2, I will represent like this. Okay, here you can see. Then in order to showcase the vectorized representation, like if I wanted to show like all the activations with respect to the layer 2, I will represent as A of 2. Okay, means all the activation with respect to the layer L I will represent as A of L. Okay, in the same way, in order to find out the activations, we need to first compute the linear computation. So into the same way, in order to find out the linear computation with respect to the all neurons into the layer L, I will represent it this like Z of L. So for example, if I say the Z of 2 means the linear computations with for the all the neurons into the layer 2. Okay, means this layer. Okay, then in order to showcase the theta with respect to the layer L, I will represent as theta of L. Okay, and it having the dimensions it having the dimensions S of L plus 1 means the number of the neurons into the next layer by number of the neurons into the current layer plus 1. Okay, it having means it having this dimension. Okay, so you just keep all this notation into the mind, because we are going to be used into the further intuitions. Okay, so let's start with the cost function inside the neural network. Okay, so as I said, yeah, so here also I will just give the notation. So here the L is equal to 3. Okay, and this is the our L1. Okay, and this is our L2, and this is our L3. Okay, and here like the number of neurons into the first layer are 3, number of the neurons into the second layer are 4, and the number of the neurons into the third layer are 2. Okay, and here actually I will one assumptions actually I will do. So on the each of the neuron we are applying the logistic function. Okay, so here I am using the logistic function as the activation. Okay, so here in order to find out like the cost function, and as I said, we are assuming like the logistic function is applied to the each of the neurons here. So first we need to understand like first we will just recap like what is the cost function for the logistic regression. Okay, so this thing I already explained into the previous videos. Okay, so we will just recap like how to compute the logistic cost function. Okay, so this logistic cost function actually it is computed as minus 1 upon m. Okay, means average over m example, summation of I is equal to 1 to m. Okay, then y y of log h of theta xi. Okay, plus 1 minus y I of log of 1 minus h of theta xi. Okay, so here like this yi is nothing but the ground truth with respect to the ith example. Then I am then log of h of theta xi means the log of prediction for that particular ith example, plus 1 minus y of I means 1 minus the ground truth at ith example, and log of 1 minus h of theta xi means log of 1 minus prediction at ith example. Okay, so this is the cost functions actually it is there with respect to the logistic regression, and into this cost function the regularization terms actually it will get added like gamma divided by 2m summation of I is equal summation of j is equal to 1 to n, then L2 norm of theta j square. Okay, so this regularization term actually it is applied to the cost function only, and this is helps to reduce the overfitting. Okay, so this the separate session actually we will take on this regularization thing. Okay, and you just keep in mind like this whatever this parameter gamma it is there, it is used as the regularization parameter, and it is applied to the all the parameters means all the weights. Okay, which is represented as the theta j, and n is here, n is nothing but the number of the features. Okay, so this is the logistic function activation. Okay, so now like in the neural network like how actually we will apply. Okay, so this is kind of become like we can say the logistic cost function for the single neuron, but here if you can see we need to apply to the neural network. Okay, so inside the neural network whatever the output it is there, it is depends on the number of the neurons present into the last layer. Okay, because in the neural network whatever the output it is there, it can be one or it can be multiple. It is depending on the number of the neurons which is present into the output layer. Okay, So while computing the cost function, we need to consider this also, like we need to compute the cost function with respect to the each neuron which is present in the last layer. Okay, so that can be multiple. Okay, so means what actually we need to consider, whatever the neurons which is present into the last layer, that actually we need to consider. So number of the neurons into the last layer. Okay, L means number of the layers, and in this case the L is the 3. So number of the neurons into the last layer in this example are the 2. Okay, means whatever the cost actually we are going to be design, it is depends on this 2 neurons. Okay, and whatever this output layer neurons are there, number of output layer neurons, I will represent at the K. Okay, so now this cost function which is we used for the logistic regression, and if we are going to apply the same cost function to the neural network, then it will looks like this. Okay, I will use a different pen. Okay, so it will looks like for the neural network, it will looks like minus 1 upon m. Okay, then in the same way, summation of I is equal to 1 to m. Okay, m is nothing but number of the example. Then as I said, we need to consider the number of the neurons into the present into the last layer. Okay, so we need to iterate over that also. Okay, so summation of K is equal to 1 to number of the neurons which is present inside the last layer. Okay, which is represented by the S of L. Okay, L is nothing but L is denoting the last layer only. Okay, so this will become Y K of I. Okay, means Y subscript I K. Okay, like the ground truth for the ith example at the neuron K inside the last layer into Yk of I log of h of theta x superscript I subscript k, which is denoting the prediction for that ith example at neuron K into the last layer. Okay, so this is the first term, then the plus 1 minus y superscript I subscript k, means which is denoting again 1 minus ground truth with respect to the ith example at kth neuron into the last layer. Then the next term is the log of 1 minus h of theta x subscript I, okay, and superscript I and subscript k, means log of 1 minus prediction for the ith example at the kth neuron into the last layer. Okay, then again, as I said, we need to use the regularization term, and regularization term actually it is applied on the all the weights. Okay, so into the neural network, the weights are associated with the all the layers. So here actually we need to consider the layer also. Okay, and with respect to each layer, whatever the weight parameter is there, it is having the 2D dimension, like the number of the neurons into the next layer by the number of the neurons into the current layer plus 1. Okay, so that also we need to consider. Okay, so this regularization term, it is gets applied as gamma divided by 2m. Okay, so first thing, like we need to iterate over all the layers. So L is equal to 1 to all the layers. Okay, then we need to iterate the for that particular layer, we need to iterate with the theta parameter also, means nothing but the weight parameter. And for that weight, the first dimension is the I is equal to 1 to the number of the neurons into the next layer, means which is nothing but L plus 1. then we need to iterate the second dimension, which is nothing but j is equal to 1 to the number of the neurons into the current layer plus 1. Okay, then we need to apply here the theta L2 norm of the theta ij. Okay, so this is denoted by this symbol L2 norm. Okay, so this is kind of the overall the cost function for the neural network. Okay, so I know it is like the difficult to understand, but just we need to keep in the mind, like in the neural network we need to compute the cost with respect to the number of the neurons into the output layer. So because of that, this term gets added, like summation over k is equal to 1 to the number of the neurons into the last layer. Okay, all the things are the same only as the logistic regression, but just this kth term only actually we need to consider. And with respect to the regularization term, okay, with respect to the regularization term, like the regularization term is applied to the all the layers. So because of that, we need to iterate over all the layers, and inside the each layer the theta parameter, it having the 2D dimension. It's the first dimension is from the I is equal to 1 to the number of the neurons into the L next layer, and j is equal to 1 to the number of the neurons into the current layer plus 1. So because of that, these three things actually it is came. Okay, so yeah, so this is all about the cost function inside the neural network. Okay, I hope you understand. Okay, so now we will go to the backward propagation. Okay, so means whatever the cost function actually we computed into the previous slide, okay, it is nothing but like it is giving like the difference between the actual ground truth and the prediction. Okay, so inside the backward propagation, like it will optimize that particular cost function. Means this is the algorithm, like it will update the each layer weights in such a way that whatever the cost function whatever the cost actually we computed with the cost function, that will gets minimized. Okay, so why actually it is called as the backward propagation? Because all the computations it will happen inside this backward direction. Okay, means from this layer to this layer. Okay, like in the backward propagation. And inside the forward propagation, all the computations actually it is happening in the forward direction. Okay, so like the first step inside the backward propagation, like as I said, like we need to compute first cost. Means the first step is like we must know like what is the output activations. Okay, so first thing, like it needs to be compute the forward propagation. Okay, so once you computed the forward propagation, then you will get the activations of all the activation of all the neurons with respect to the output layer. Okay, then the second step inside the backward propagation, like it will compute the cost. Okay, it will compute the cost function. Okay, and inside the third step, like what will happen, like it will update all the thetas with respect to the each layer as, okay, theta L, okay, minus alpha, which is nothing but our learning rate. Okay, then partial derivative with respect to the theta I j for the partial for the cost function. Okay, so why this ij is become? Because all these layers, means whatever the weight associated with this layer, it having the 2D dimension. Okay, because of that this ij actually it is came. Okay, means internally it is ij only. Okay, so these are the like the very high level steps are there inside the backward propagation. Okay, so as I said, like the first step inside the backward propagation, like we need to first compute the forward pass, then we need to compute the cost function, and we need to find out the in order to update all these theta's parameter, we need to find out the derivative with respect to the cost function. Okay, so how actually we are going to do? Okay, so I will explain with the example of this. Okay, where it having the 1 2 3 4 means L is equal to 4. Okay, so yeah, so let's do it, like how the backward propagation we are going to compute. Okay, so as I said, we are going to the first step. Like first we will find out the forward propagation. Okay, okay, so as I said, the forward propagation, it will be happen in the forward direction. Okay, so first we need to compute the activations with respect to the layer 2. Okay, so this is the layer 1, this is the layer 2, this is the layer 3, and this is the layer 4. Okay, so first we need to compute the activation with respect to the layer 2. Okay, so in order to compute the activation with respect to layer 2, first we need to find out the linear computation with respect to the layer 2. Okay, which is denoted by the z of 2, and it is computed as theta. Okay, L minus 1, so 2 minus 1, it has become theta 1 into, okay, the matrix multiplication by A of 1. Okay, so here A of 1 is nothing but this input layer features only. Okay, so with this thing we will get the linear computation with respect to the layer 2. Then we will find out the activation with respect to the layer 2 by applying the activation functions on this linear computations. Okay, so like that we will get this thing. Okay, so once we will get this thing, then we will move to the next one, which is nothing but linear, which is nothing but activation with respect to the layer 3. Okay, so yeah, I will use different pen. So in the same way, in order to find out the activation with respect to the layer 3, first we need to find out the linear computation with respect to the layer 3. Okay, and this is computed by theta 2 into A2. Okay, which is nothing but this only. Okay, and once we will find out that, we will compute the activation with respect to the layer 3 as applying the activation function on this linear computation. Okay, then we will get this thing. Okay, then in the same way, we need to move the forward, we need to find out the activations with respect to the layer 4, and how we will find out in the same thing. Actually, we will find out. Okay, first we need to find out the linear computation with respect to the layer 4, and how we will find out theta 3 into A3. Okay, and in the last we will find out the activation with respect to the A4, activation with respect to the layer 4 as applying the activation function on this linear computations. Okay, like that we will get this. Okay, yeah, so once you get the forward propagation, then need to be compute the cost function. Okay, so the cost function, how actually it will get compute, it is gets computed by this formula only, as I said. Okay, and after that the next step is like we need to find out this term. Okay, and derivative with respect to the cost function for the theta ij. Okay, like we computed the forward propagation means activation with respect to this output layer, along with the cost function is also we computed. And now the thing is like we need to compute the all the derivatives. Okay, so with respect to that, like what actually in the backward propagation we need to do, we need to find out the delta. Okay, let me select my pen. Okay, So in order to compute the derivatives, what we need to do, we need to find out the delta at jth neuron into the layer L. Okay. So what is actually it is there? So it is nothing but the error, okay, with respect to the jth neuron into the layer L. Okay. So this means if I wanted to showcase like the error with respect to the this first neuron into the last layer, which is nothing but L4. Okay, this is the L3, this is the L2, and this is the L1. Okay, so in order to find out the error with respect to the first neuron into the last layer, which is the layer 4, I will denote is that delta, okay, delta superscript 4, okay, because it is the fourth layer, and subscript 1. Okay, so in order to find out the error with respect to the first neuron into the last layer, I will compute as, okay, activation, okay, at fourth activation in the fourth layer at the first neuron, okay, minus actual prediction in the fourth layer at first neuron. Okay, so in this way I will get this error with respect to this neuron. Okay, so this thing only if I present into the vectorized representation, so this will become like delta with respect to the fourth layer, means all the errors with respect to all the neurons in the fourth layer I can able to compute by activation in the last layer, which is nothing but the fourth, minus whatever our ground truth at the fourth layer. Okay, so in this way I will get the delta 4 whose error, which is error with respect to the fourth layer. Okay, so once you compute this thing, okay, so in the, as I said, the backward propagation will be happen in the backward direction. You need to jump to the next layer, backward layer, which is nothing but delta 3. Okay, so in the next thing, like how you will find out the delta 3. Okay, so the delta 3, it is gets find out by delta 3 is equal to theta 3 transpose, okay, then matrix multiplication with delta 4, okay, then element wise multiplication by, okay, derivative of the derivative of the activation function which is applied to the linear computation of the layer 3. Okay, so this term it is there, it is derivative with respect to the activation of linear computation applied to the this layer 3. Okay, so again this actually this derivative of Z3, it is we can able to compute it as activation with respect to the third layer, then into 1 minus A3. Okay, so when actually we will solve this thing, it will means we will end up with this formula. Okay, so like that we will get the delta 3, okay, which is nothing but this. Okay, then in the same way, now again we go to the one step back into the backward direction. We need to find out the delta 2. Okay, means error with respect to the layer 2. Okay, so this how actually we can find out in the same way only. Okay, all the patterns are same only. Okay, then delta 2, which is nothing but error with respect to the second layer, how we will find out theta 2 transpose matrix multiplication of delta 3. Okay, from here we will get the delta 3, then element wise multiplication into derivative with respect to the this linear computation of Z2, linear computation of the layer 2. Okay, and this again it will gets computed as A2 into 1 minus activation in the second layer. Okay, so this actually it will give this thing. Okay, which is nothing but our delta 2. Okay, so now like the backward propagation will be in the backward propagation all the deltas will get computed up to here only. Okay, means from the layer L to the layer this L2. Okay, means from this from the output layer to the it is not compute the deltas for the input layer, because these are the only the input features are there. Okay, there is the no deltas or no weights are there. Okay, so once you compute all these deltas, okay, then you need, then the derivative is the partial derivative with respect to the theta ij, okay, for the cost function. Okay, how actually it is gets computed as, okay, a activations of activations of jth neuron inside the layer L, okay, into this matrix multiplication of delta of ith neuron inside the plus 1 layer. Okay, so with this thing you will get that particular cost function, and this thing only you need to substitute inside this thing. Okay, theta I j. I will use the different pen if you will get better idea. Okay, this theta I j minus alpha into derivative of partial derivative of theta I j with respect to the cost function. Okay, this only you will substitute here. Okay, so yeah, so like that actually this backward propagation will be gets computed, and in this way this thetas, all the thetas actually it will get updated, okay, in order to minimize this cost function. Okay, yeah, so yeah, I hope you understood. Okay, so in the recap, if I can say, like inside the backward propagation there are the 3 steps are there. First actually you need to find out the forward propagation. Okay, then the second step you need to find out the cost function, and the third step you need to find out the derivative with respect to the cost function, okay, which is nothing but this term. So in order to find out the derivative with respect to cost function, you need to find out the deltas with respect to the all the layers, okay, in the backward direction. So here you will start with the last layer only. Okay, so the deltas are nothing but the error with respect to that particular layer, and how you will find out inside the last layer you will find out the delta of 4 as the activation with respect to that last layer minus all the ground truth with respect to that last layer. So once you will get the delta with respect to last layer, then you will go to the delta L minus 1 layer, and there you will find out the delta means with respect to the L minus 1, which is nothing but delta 3 as theta L minus 1 transpose, okay, into delta L into the derivative with respect to this linear computation, and this again it is computed by this formula, which is nothing but activation with respect to the third layer into, so this is the element wise matrix multiplication by 1 minus activation into with respect to the third layer. Okay, so the same thing in the same way, then again you need to find out the delta 2, then up to the means you need no need to compute the deltas for the first layer, because there are the not weights are associated there. Okay, so once you go to the this delta 2, then you need to find out this cost function, and this cost function thing you need to substitute into this thing. Okay, then you will get the final thing, and you can able to update all the theta ij minus learning rate into that particular substitution value of partial derivative of the cost function. Okay, so these are like the steps are there. Okay, I hope you understood. Okay. Okay, so now the next topic is the gradient checking. Okay. Yeah, so so the gradient checking is the algorithm like when you implement the backpropagation from the scratch. Okay, so at that time, in order to validate your implementation, actually this gradient checking we need to do. Okay. So in this thing, like what actually we need to do. Okay. So once you implement your backward propagation, and you will update your thetas to the sum of the iteration, and when you plot that particular cost function, it will looks like this way. Okay, it will looks like this. Okay, so this is the thing but our cost function, and here all the thetas are there. And if your algorithm means whatever the backpropagation it is implemented from the scratch, it is kind of working good, means it is correct implementation, then it will looks like this. Okay, and here whatever the derivative with respect to the cost function, it is nothing but the tangent to the, means in the first lesson I told already, this is nothing but the tangent to the slope of this cost function. Okay, like this. Okay, so into the gradient checking, like what actually we need to be checked. Okay, so here actually I made one statement like the derivative of the cost function is nothing but the tangent to the slope of this cost function. Okay, means if I can say like yeah, means in the gradient checking, actually what they are doing, like they are making one kind of assumption, like if your backpropagation is kind of very correctly implemented, then the derivative with respect derivative with respect to the cost function, okay, it is the nearly equal to this particular slope. Okay, means this one. Okay, so in order to prove this thing, actually what we need to do, we need to consider suppose this theta actually I am considering, and we need to consider one small epsilon value. Okay, sorry, we need to consider one small epsilon value, which is 0.0.001. Okay, and with this epsilon value, like whatever plus epsilon, and this is suppose our theta is there, and this one is the minus epsilon. Okay, like here. Okay, this is also epsilon, plus epsilon, and minus epsilon. Okay, so here actually we will get the width. Okay, then in order to compute the slope, height, because slope is nothing but height divided by width. So width I will get like with this 2 epsilon, and in order to compute the height, so it is nothing but, okay, so here you can see, okay, this is the cost with respect to the theta plus epsilon. Okay, because here the epsilon is there, and theta plus epsilon, then plus minus cost with respect to the theta minus epsilon. Okay, which will give this point. Okay, because theta minus epsilon is here, so it will give this particular height thing. Okay, and with divided by the 2 epsilon, we will get the width. Okay, means it is nothing but this slope only. Okay, so when this equation is gets correct, like derivative with respect to the cost function for this theta, when it is closely equal to the slope, okay, then only we can say that our back propagation from the scratch, it is accurately implemented. Okay, so in order to check, in order to validate that thing, this gradient checking actually they are doing. Okay, so this is kind of the optional thing. Okay, so you have to know, like if you implement the gradient descent from the back propagation from the scratch, then in order to verify your implementation, this thing actually you need to do. Okay, let's move to the next topic, weight and the bias. Okay, so this is kind of a very common question asked by the interviewer, like what is the significance of the weights or the bias in the neural network. Okay, so let's understand this. Okay, so whatever the weights are there, like what actually it is doing. So weights will give the strengths to the connection between the neurons. Okay, what is exactly mean of that? Okay, so weight either increase the importance of the feature or it will decrease the importance of the features. Okay, so if I say like weight is equal to 0, then if the means whatever the value associated with that particular input, it is having the 0 importance. Okay, means it is nothing contributing in order to generate the output. Okay, so if your weight having the value as the negative, then if you increase the input feature associated with that weight, then the inside the output, it is decreasing its importance. Okay, then if you having the weight, it is kind of the positive, then in the same way, if you increasing the value of the input feature associated that positive weight, means you are increasing the importance of that feature in order to generate the final output. Okay, so this is kind of the means I can say, like in that way it is providing the strength to the connection between the neurons. Okay, so in order to understand, I will give one example. Okay, so suppose you are working on like suppose cat and dog classification. Okay, and you're having the neural network in which you are the providing the features like the nose of the cat or dog. Okay, the eyes of the cat or dog, or the ears of the cat or dog. Okay, and these features actually it is input to the one of the neuron. Okay, and here you found out like whatever the eyes of this cat of dog, it is kind of having more importance than the nose and the ears, because it is kind of the differentiator in order to recognize that particular image, it is either from the cat or dog. So in that way, you need to give the more weight to the eyes. Okay, for example, if I give the weight, means if all the weights are in between 0 to 1, and if I give the weights here 0.6 to the eyes, weights 0.2 to the nose, and 0.2 to the ears, then here, like in order to generate this final output, whatever the eyes feature is there, it will contribute more. Why? Because it having the more magnitude or the more value. Okay, so in that way, like the weight it can able to, as I said, the weight it can able to increase the importance of the input feature or the decrease the importance of the input feature. Okay, and also like inside the means when you are fitting the hypothesis in the back propagation, so at that time whatever the weights are there, like it will help to move the hypothesis into the vertical directions. Okay, now let's understand like what is the bias. Okay, so whatever the linear computation inside the neural network, it is computed by the line equation, which is denoted by the y is equal to mx plus c. So where whatever this m, it is nothing but that this is the weight, and this constant c value is nothing but the bias. Okay, so why actually bias? Actually, it is used inside the neural network. So bias will give the extra flexibility in order to make your hypothesis in order to fit more. It will give the more flexible based fit to the your data set. Okay, so how actually it will be give? So if you can say, like as I said, whatever the weight parameter is there, it can able to move your hypothesis in the vertical direction. Means with the weights you can able to move your hypothesis in this vertical direction only. But when you will consider the bias thing, you can able to, means we can able to give the more extra facility in the terms of, like we can able to move the hypothesis in the forward or into the backward direction also. Okay, with respect by using the bias parameter. Okay, so when you are dealing with the very real-time example, so at that time whatever our data points are there, means whatever the best fit hypothesis is there, it is not always in line with the origin. Okay, because when you are using only the weight thing, then you can, then at that time your hypothesis, it can able to move in line with the origin, either vertical or the directional. But what if whatever your best fit point it is there, it is not in line with the origin, it is somewhere here or somewhere here or somewhere here. So at that time when you are only using weight, so at that time you cannot able to achieve that kind of the best fit. But when you will you use the bias, so at that time you can adding the more flexibility. So your hypothesis, it can not either it can able to move into the vertical, it can able to move the forward and the backward also, like the horizontal movements also. So you can able to get the best fit, like either here or either here. Okay, it is not limited to the in line with the origin. Okay, so because of that, actually the bias thing they are using. Okay, so yeah, so this is for the today's session. Okay, so I hope you understood all the things properly. Okay, yeah, so still someone not subscribed to my channel, so please subscribe it for the further updates. Thank you so much.